Hey programmers, Alvin here. Right now, let's go over this all tree paths problem. So we'll just start by implementing the exact solution we traced through in the approach video. So if you haven't watched the approach yet, be sure to watch it. And we said that we would solve this in a recursive way because it's probably the easiest code to implement here. So I'll start with our base case, right? We know we want to return basically every root to leaf path within our binary tree. And so my base case is going to be about a leaf node, right? Because I need a path just to a leaf. So what do I know about a leaf node? Well, it's going to be if the root left is null and, so I need to use my ampersand here, and root right is also null. That would mean that root right now is a leaf. Cool. So if that's the case, we said that we need to return something very particular. We need to return an array containing all of the paths for this subtree that only contains a single node, right? We said that an inner subarray here represents the path, and inside of that I put all the values along that path. So I'd put root.val here. Nice. And so what I think about is if I had a single node, then there's only one path through it, right? Just taking that one value. So let's say that single node was z, the path would look like that, right? So that's why I'll return it like this. So that's our base case that kind of will help us begin constructing our paths. We also need to handle the case, all right, like we usually do, recursively, what if the root itself is going to be null, right? So if root is null, then what I need to do is return all of the paths through that tree, right? If I have null, that means an empty tree. Well, then there are just no paths, right? So the outer array here, that's the collection of paths for which there are 0, right? There's no subarrays here, there's no paths. And whenever you have multiple base cases, you may want to actually verify, what's the correct order of writing them. So I know that if root is null right now, then I would check null.left, and again, error in JavaScript, right? No property left of null. And so I will have to flip this around. I want to guard with the null check up front. So that'll be much more robust. All right, so now that we have our base cases, I think, exactly what we said in the approach video, let's work on our recursive calls, right? And here's where it could get a little tricky. What I like to do is just lay down my core foundational patterns, and I'm going to build around it. So if I'm just committing to doing this recursive means you call the same function. And you know that you're going to have to call recursively on your left and right children. So root.left, something similar for root.right. Now I'll think about what type of data I get back from these calls, right? What I expect back is a 2D array. A 2D array representing all of the paths through that subtree, right? So what I'll say over here is, maybe I'll put this in a variable just to label it, and I'll say const, we'll say left subpaths, and I'll say const right subpaths. And just in a kind of mental model sense, let's say I had, I don't know, this as an example. So I'm going to steal this little snippet here just so we can visualize it. So let's say that right now my root is A. When I call upon all tree paths of root.left, I'm going to assume that this function works, right? I got to take my recursive leap of faith. So I would get back an array, a 2D array, representing the paths through this subtree of B, D, E. And what that ought to look like is this, right? So it's going to be a 2D array, and it's going to have a subarray of BD, and also another subarray of BE. Right? So I expect that to be the data for my left subpaths. And for my right subpaths in this particular scenario, it would just be an array of CF. So very similar shape, but there's only one path through that subtree. So just like this, CF. Cool. And this is a trick, or really just a tip, that I find useful, right? Sometimes it's hard to like visualize the abstract way this works, so I kind of plug in an example. And if I make it work in a general sense for that example, then it should work for most inputs, right? So I'm going to imagine that I get these two subarrays as my left subpaths and right subpaths. And I think about what I need to do with them. Well, I need to just basically add A, or my current root.val, to the front of each subpath, right? So let me go ahead and do that. So let's say I do it for left subpaths. I'm going to have to gather up these completed paths in some array that I eventually return. Maybe I'll create that over here. So I'll say just paths possibly over here. And then by the end of my function, I know I'm going to return it. So I'm going to return paths. So let me start by iterating through left subpaths, and I'm going to put my current value, so root.val at the front. So I'd be putting like a in the front of each of these paths logically, right? So we'll say, I don't know, for let subpath of left subpaths. So here in JavaScript, I'm just iterating through every element of an array, right? So on the first iteration of this for of loop, the subpath would be this entire subarray of BDE. Next iteration would be BE, right? And what I'll do is I'll just take the elements of that original subpath, spread them out. I need to be sure that I make a copy, right? Because I'm going to need to create many different subarrays here. So I can do subpath, and I'll go ahead and put my root value at the front. So that gives me a new array where my current value of A is at the front of it, right? And then what I would do is just push that into my final paths, right? So I could say paths.push that entire subarray. Now it's completed, right? So what would happen now is I would put like A at the front of these. So we'll say A comma and A comma over here. And those would become members of this kind of running subarray. So things are looking pretty good. And I think for now, delete this little snippet. And it's just going to be symmetric for the right-hand side, kind of what we expect, right? So here, I just want to iterate over my right subpaths. And of course, I would put an A in front of this, like that. And then that becomes a member of this paths array. And by the end, it looks like paths is exactly what we need it to be. Nice. And so with all of that in mind, let's go ahead and test this code. Might have a typo. It's a decent amount of code, so we can always course correct. Nice, but it looks like we got it first try. All right, so take a moment, glance over at this code. This is a pretty important pattern in terms of like building up multiple arrays through recursion. And notice how we're able to really break this problem into, two subcalls, right? If you had access to all of the paths in your left subtree and all of the paths in your right subtree, all you need to do is put your own value at the front of each of those paths and combine them into one array. One thing you're probably noticing about this implementation is we would have O of n calls, so recursive calls, right? Just a call for every node of this tree. But if I look at especially like this code, when we create a copy of an array, we would actually incur some additional runtime there, because technically I'm iterating through all subpaths, and when I spread out the elements of a single subpath, that's another loop. And these kind of take the form of nested loops, right? Technically, this expression kind of does iterations. We've actually seen an optimization for this scenario before. If you'd like, you can totally just keep pushing your root val into the existing subpath, but then by the end of your function, you need to actually reverse those subarrays. That way you wouldn't need to actually use this spread operator. However, I'm going to leave that detail to you. So with that, I want you to make sure you can code up this solution before you go on to the next problem.